All right, in this video, we're going to apply the alternating series test to 3 different examples. We're going to use it to determine whether a series converges conditionally, absolutely, or it diverges. And then if it converges, we're going to actually try to estimate the value of the series. Okay? So we're going to do 3 examples here. I'm going to move relatively quickly, and feel free to slow the video down if I'm going too fast for you. All right, so the first one we're going to look at is -1 to the n plus 1 over n factorial. All right, and the alternating series test for checking for convergence is really easy. We just need to check if the terms go to 0. So does an equal -1 to the n plus 1 over n factorial, does that go to 0? In this case, we need to look at the limit as n goes to infinity of -1 to the n plus 1 over n factorial. And if the absolute value goes to 0, you can show that the individual terms will go to 0. And so that's just the limit as n goes to infinity of 1 over n factorial. And notice the denominator staying the same size, and the individual, or the denominator is going to infinity. The numerator is staying the same size, and so that's got to be 1 over infinity, which is 0. The answer is yes. And so by the alternating series test, it converges. And then the question is, does it converge conditionally or absolutely? And to answer that question, we have to look at the series with and without absolute values. Now, we know without absolute values, where it's actually alternating, it does converge. What about the sum of just 1 over n factorial? Does that one converge? Well, that one's a little bit trickier, but I think we did look at this in a previous video, and we did that by comparing it, because n factorial is much bigger than, say, n squared, which means that 1 over n factorial is much less than 1 over n squared. And so therefore the sum of 1 over n factorial is less than the sum of 1 over n squared. But we know that converges. Right? That's just a p series with p equals 2. And so this must converge as well. And that's by the comparison test. And it was a direct comparison. Okay, so we just checked 2 things. We checked when it alternates back and forth, it converges. And we showed that when it doesn't alternate back and forth, it converges also. If it converges both ways, then we would conclude that it converges absolutely. Okay? All right, so that was the first part of the question. Determine if the series converges. And if it does, does it converge conditionally or absolutely? And we did that. We showed that it converges absolutely. So then the question is, how far do we have to go out in the series to be able to estimate it within, let's make it a little easier on ourselves. Let's make that 0.01. Okay? All right, so how do we estimate the sum of 1 over n factorial from n equals 1 to infinity to within 0.01? All right, and the idea is we know that the partial sums get closer to the true value. And if we can find the first term that is smaller than 0.01, then we can conclude that corresponding partial sum was a good enough estimate. All right, so ultimately we need to look at where is the absolute value of an plus 1 less than or equal to 0.01. All right, and so we're looking for a term where the factorial, which is 1 over n factorial, is less than 1 over n factorial is less than 0.01, or another way of saying that would be, well, that 0.01 is 1 over 100. So we could say that 100 is less than n factorial. And well, that's an equation that you can't really get n by itself very easily. But factorials are actually not so bad to compute by hand if the numbers are relatively small. So let's compute some factorials for ourselves. 1 factorial is just 1. 2 factorial is just 2 times 1, which is 2. 3 factorial is 3 times 2 times 1, which is 6. 4 factorial is going to be 4 times 3 times 2 times 1, which is 4 times 6. And notice each one is going to be just multiply one more number than the previous line. So 5 factorial will be 5 times 24, which is 120. And so you'll notice that 5 factorial is greater than 100. And I realize I made a little mistake there. Let's fix that. 1 over n plus 1 factorial would be the absolute value of an plus 1. And so if 5 factorial is greater than 100, then 1 over 5 factorial is less than 0.01. And so that corresponds to n equals 4. Okay? So A5 is less than 0.01. And what that means is that the true sum minus the fourth partial sum is also less than 0.01. Right? We proved that in the previous video, or at least we explained the reasoning behind that the terms are alternating back and forth. We know we overshoot every time. And so if I go from S4 and then I add the next term, A5, I know that's going to take me too far. And so S4 must have been closer to the true sum than A5. Okay? So S4 is not a bad estimate for the true sum. And what is S4? It's 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial, which is 1 plus a half plus a sixth plus 1/24. And that is going to be a pretty good estimate for what the sum converges to. Okay? All right, so there's one example. All right, let's do another one. The next one we wanted to look at was negative 1 to the n plus 1 times 2 to the n over n. So negative 1 to the n plus 1 times 2 to the n over n. And we'll first check to see if it converges. And the alternating series test requires that we show that the terms go to 0. So let's look at the limit as n goes to infinity of the absolute value of an. The limit as n goes to infinity of, well, if you take an absolute value of those terms, the negative 1 term is just going to become a positive 1, and we'll have 2 to the n over n, which looks like infinity over infinity. That's indeterminate. However, we can apply L'Hopital's rule to that, and we will get 2 to the n times log 2. That's the derivative of the top, divided by 1, which is the derivative of the bottom, which gives us infinity. And so the terms do not go to 0. And if the terms do not go to 0, then we can conclude that it diverges. Diverges. And in this case, that's by the nth term test. Now, let me remind you, the alternating series test and the nth term test sound very similar. So you're probably going to want to review those carefully and make sure you understand the difference. The nth term test says if the terms do not go to 0, then it diverges. The alternating series test says if the terms are alternating and they go to 0, then it converges. So the fact that they're alternating is important. That's the only way that it allows us to conclude convergence. In this case, since the terms do not go to 0, well, the nth term test was sufficient. And if it diverges, there's no point in estimating it. We just know that it goes off to infinity. All right, on to our last example. And that one was negative 1 to the n plus 1 over the log of n. And we want to check to see if it converges. And in this case, we'll again look at the limit as n goes to infinity of the terms. It is alternating, so alternating series test applies. And if you take an absolute value, we'll just have 1 over log n, or 1 over infinity, which is 0. And since the terms are going to 0, we can conclude, so this converges by the alternating series test. Okay, now on to the next question, which is, does it converge conditionally or absolutely? We know it converges when it alternates. What about if it's not alternating? What if we made the terms positive? So let's look at the sum of 1 over log n. And this is also an example we've looked at previously. And let's assume, let's say that n is going to go from 2 to infinity. The reason I'm going to put a 2 there is because we would have division by 0 if we started with n equals 1. So 1 over log n, that is definitely not geometric. It's not a p-series. It's not telescoping. It also would be hard to integrate. So I'm going to suggest that we should look at a comparison test. And the comparison that we can make is that log n is not greater than, is less than n, which means 1 over log n is greater than 1 over n. And we know something about the sum of 1 over n. It diverges, right? That's our famous harmonic series, or p-series with p equals 1. And, well, if you're bigger than something big, you're also big. And so this diverges. And so we would conclude that the sum that's alternating well, it converges when it alternates. It doesn't converge when it doesn't alternate, so it converges conditionally. Okay. All right, so one last part. Now that we know that it converges, we'd like to know, well, how far out in the series do I have to go so that my partial sums would be a sufficiently good estimate? And so what we're looking for is, we know that the error in an approximation for our partial sums is less than the next term. And we want that to be less than or equal to 0.01. All right, so let's compute the absolute value of an plus 1. So the absolute value of an plus 1 is equal to absolute value of negative 1 to the n plus 2 over log n plus 2. Absolute value of the top is going to make that a plus 1. The bottom is already positive. Okay, and so we want that to be less than 0.01, which is just 1 over 100. And so we could rearrange that equation just a little bit and write it as 100 is less than log n plus 2. And if we want to know the value of n, we can try to get n by itself. If we raise both sides to the e, that'll cancel out the log, and so we'll have just n plus 2. And so we'd say that n must be greater than e to the 100 minus 2. So if I compute Sn for some value of n larger than that, then that would be a sufficiently good approximation to S. Now, e to the 100 minus 2. Any idea how big of a number that is? Well, let's see what happens when we type it into Google. E to the 100 minus 2. 2.69 times 10 to the 43rd. That is an astronomically large number. Huge, unfathomably large. Okay? And so what that means is, in order to estimate this sum correctly, we would need something like a partial sum involving, well, 269 with like 40 some zeros. after it. So there's going to be 41 zeros. We would need to have a partial sum that big to be confident that we're close to the true value. So I will not actually go through that calculation, but I want you to recognize is that alternating series converge, but they may converge very, 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 very slowly. In this case, in order to get a reliable estimate for what the true value is, it requires an incredibly large amount of terms. And so, although in principle, we now know how to estimate the value of this series, in practice, we can't actually carry out those calculations. And so I won't even try. All right, so big picture, what can we do with the alternating series test? We can check to see if something converges. And once we know whether it converges when it alternates, we can apply some of our old techniques to see if it converges absolutely or conditionally. Once we've done that, we can also try to estimate the value of a sum, and that involves comparing the next term to whatever tolerance we want. So if we want to be within 0.01, we look for the first term in the series, where all subsequent terms are going to be less than 0.01. Okay, so that's the big idea. I will stop here, and in the next video, we're going to talk about some of the interesting implications of conditionally convergent series and alternating series.